That was really hammered home.
So we're gonna get started. The first stuff that we do today is finish the discussion of the question. And the second half will be used for lab 3, which I posted on Moodle. And I said before, lab 3 is actually replicating one of the studies in the paper. So hopefully you can get a full experience of understanding Gibbs sampler and all that. So a couple of things, I guess nobody responded to question 4, which is fine. And it's not one of the other ones to do. So we're gonna skip it for now. And I noticed many of you, I think, talked about 6 and 7. Yeah, so maybe we're gonna start with those, and then those again, I think, are talking about like the procedure and then comparison, all that. So question 6 is a defining characteristic of the Gibbs sampler is that it always uses a full set of univariate conditionals to define the iteration. Explain this claim by illustrating how the Gibbs sampler works with k parameters. Okay, so generically we have theta 1, theta 2, until theta k. And yeah, so just imagine on a particular iteration what you would do. And one thing I would say before we break for a smaller group discussion is be super careful when you're adding like those iteration index to the parameters. So when you're talking about like say how for a particular iteration, how you generate the k parameters in a row, make sure that you also add the iteration index for the parameter that you're working with, because that's very important. Okay. All right, I'm gonna break for a few minutes so you can chat with your neighbors about it, and we're gonna look at it together. I would say this is probably also related to one of the midterm questions. So I think going over through this and now is good because you will be allowed to do exam corrections afterwards. So like, let's focus on how to solve this. Okay. All right. Sounds like everybody's ready to talk about this. So yeah, anyone wants to start? I guess yeah, talk about say if you have k different parameters in the model, generic k, generic theta here. Let's just say at a particular iteration maybe s, small s. I think that's what we typically use. So what would you do to do a iteration for this set of parameters?
Well, you would start with like theta 1. You would use your full conditional posterior distribution to get a value with the s minus 1 of all the other parameters.
So let me just write, I guess, I will just use this pi, represent the full conditional posterior distribution, and I guess it's theta 1 even. So in this case, at a particular iteration, so it's important to add the iteration index here. Okay. In a sense that right now we only have flaws of the remaining theta 2 to theta k from the previous iteration, right? So so that's pretty important. And okay, so I think that's good when we get the first theta 1s. So what about theta 2?
And then for theta 2, you would use, it would be the same except theta 1 would be theta 1s instead of s minus 1.
Exactly. So when you have multiple parameters, in this case it's k, make sure that when you update one of them, you're using the most updated one at the iteration for the remaining parameters. Okay, so that's why earlier before we broke to smaller group discussion, I was talking about that you need to be super careful when you're adding the index, okay, the iteration index. And this actually happened, if you remember, when we were coding up the Gibbs sampler by ourselves, we have those like a chunk for one parameter, right? And then we make sure that we give like the correct parameter name so it can be used for the next like parameter. So I think the example that we saw is the mu and the phi, right? So we make sure that we assign the value of mu after we draw it at this iteration, and we use it immediately after when we're drawing phi. Okay. All right. So I guess the rest will work as follows. So I will just maybe also just write about theta 3. So this is the full conditional posterior distribution, and now we have the most updated theta 1. We also have the most updated theta 2, but the other ones are still at the previous iteration. Okay. So this is where you see that in this case, you are taking the current iteration draws of theta 1 and theta 2. Okay? So if you keep doing that, the last one, theta k s, will be the full conditional posterior distribution of it. And then now everybody else or everything else is at the current iteration. All right? Yeah.
Would it be k minus 1?
Oh, yes, k minus 1. Thank you. Yeah, so this will be the process of doing one iteration of the Gibbs sampler. And I should mention that the order, I guess, doesn't really matter. Like if you want to update theta 2 first, yeah, feel free to do that. And I think in our example in class, we looked at whether you update mu first or you update p first. So in the end, if you run the Gibbs sampler, you will see that the results will be very similar to each other. There will be some slight difference because of the randomness. Other than that, the order wouldn't matter as well. Okay? All right? Okay, so I think this one is good. And let's come to question 7. Let's summarize different approaches to sampling the Gibbs sequence. And we'll give you a few more minutes to discuss. You can look at people's responses on Moodle if you want, and we can check about it in class together after a few minutes. I think maybe that's from some of you ideas to summarize the different approaches to sampling the Gibbs sequence. I think the paper actually talked about multiple, so or based on what we discussed in class. Do you see different approaches to do that? And if you summarize, maybe just talk about their differences and similarities.
So the paper said that you could pick some large value k and only look at the iterations after that. So that's like the Vernon approach that we talked about in class, except for the Vernon parameter, you're specifying a proportion that you're going to discard. Then they also talked again about what we talked about last time for question 2, the Gelfand and Smith approach. So you run M independent chains and just save the final values from each chain to create your sample. They also talked about you could just run a long chain and save every arc value, which is the thinning approach we talked about.
Right.
And then they said if you're really worried about how computationally intensive it's going to be, you can just run it and save all the values, but then you will have a dependent sample. But it should still converge.
Yeah. Make sense? Yeah, so I guess the biggest two is running M independent chains or running one long chain and then do the thinning. Okay, so when they do the thinning, and I guess Vernon in this case as well, they're trying to make sure that even if you're doing this long chain process, you will get M independent draws. Okay, so at the end of the day, we know that the Gibbs sampler is trying to get independent draws or almost independent draws. So if our goal is to get M of them, either you run a super long chain, right? Do the burn-in, do the thinning so you get M independent draws in the end, or you run M independent chains and only save the last draw. Okay? So the burning and thinning, I think this also relates to question 2, like Caroline was talking about last time, that the burning and thinning in some way probably only applies in the super long chain case, because you have to chop out maybe the first 50% and then thinning every 50 iterations. And for the M independent chains case, I think they usually talk about like length of K, so it's K iterations for each. And even though there's no explicit, I guess, burning and thinning process is sort of done there, okay? Because you throw away every other iteration except for the last one, so that's clear burn in. And there's no need to do thinning in that case because you're only saving the last draw, because the thinning is really just trying to get independent out of dependent draw. Okay, so I think those are good things to keep in mind. In terms of what we need to do, you feel free to do whatever, and you will notice that like last time we were talking about JAX, right, the software, and then you can actually pretty easily define how many you want to burn, right, how many you want to thin. And we also talked about MCMC diagnostics. So those are important graphs or like summary statistics to look at. So you can verify whether you are getting independent draw from the posterior. Okay. All right, I think that's for 7, which is good as well. And I was mentioning that nobody responded to 4, and even for 5, I think very few of them responded. So I'm hoping maybe we're just going to postpone this for Thursday, so we have a quick discussion at the beginning. And some of you, I think the responses that we have on question 5 are actually pretty good. Like I can see that it's typed up in LaTeX, all that, and it's clear. So take a look. It's pretty clear. I mean, once you go to Moodle, you can see others' responses to question 5. So we're gonna discuss that on Thursday. And if you get the chance, if you want to respond on question 4, feel free. And but on Thursday, we're gonna just discuss it in class as well. Okay. All right. Good. So I think that's for the paper discussion part. And now we're gonna go to lab 3. So let me bring that up for us.